Well, hello and welcome to Module 2. We'll get started today with Optima Prime and her transformers, the Shifty Wives. So Optima Prime is designing a robot quilt for her new grandson, and she plans for the robot to have a square face, meaning the length and the width will be identical, right? So the amount of fabric that she needs for the face will depend on the area of the face. So Optima decides to model the area of the robot's face mathematically. She knows that the area A of a square with side length x units, which can be inches or centimeters, is modeled by the function A of x equals x squared units. So let's just do a little diagram first. That's going to be a square like this that's x by x, right? So it's x squared. So now what we need to look at is what is the domain of the function a of x in this context? Well, if we're looking at the domain of a function with real dimensions, that means that we must have positive dimensions, right? So we can't have a square with a negative side length. So what that means is that our domain is going to be from 0 to as big as she can make it, which we'll say, just for fun, is infinity. So the domain is equal to 0 to infinity on the x-axis. So what you need to do for just a second is thinking in terms of this square idea. I want you to match up each of these statements with these letters over here on the right. So go ahead and take time with your partners at your table to match up those statements, referring to this picture kind of diagram up here. See if you can make a match. Take 2 minutes to do that. Okay, hopefully you have something jotted down there. So let's go through these and talk about them. It says the first one says the length of each side is increased by 5 units. Well, if I think about the length of each side is x, so if I'm going to increase it by 5 units, that's just x plus 5 and x plus 5. Because of that, my area now is x plus 5 times x plus 5, or more simply, x plus 5 quantity squared. So we know that this first one is b. Now the length of each side is multiplied by 5 units. Well, if I take the length of each side and I multiply it, it's just 5 times x, 5 times x. So what I'm actually doing now when I'm multiplying those together is 5 times x, or 5x, times 5x, which is the same thing as 5x quantity squared. So notice that I have to have that within the quantity because that is different from 5x squared like up here, right? So the second one will be C. Now the area of the square is increased by 5 square units. So think about this. We have the square, and then after it has been squared, after we already have the square, we add 5 more square units. So that's actually going to be D right here. It's not dealing with the linear factor anymore. It's dealing with the square factor. So once we're in the square dimension, then we add 5. And the last one, oh, I guess I could write just D. And the last one is, I meant to put that right there. The last one, the area of the square is multiplied by 5. So we already have our square, and then we multiply it by 5. That will leave us with our last one that we have, A. So now we're going to start thinking about the graph of y equals x squared. And here we're going to actually look at it in the domain of all real numbers rather than just our positive numbers. And we're going to look at how the changes of the equation that we made, like adding 5 or multiplying by 5, affect the graph. So Optima decided to make predictions about the effects and then check them out. So what I want you to do is to predict how the graphs of each of the equations will be the same or different from the graph of y equals x squared. So things that would be the same or different are things like, well, is it still the shape of a parabola? Is it opening upward? Is it opening downward? Is it thinner? Is it squattier? Does the vertex or the origin of the actual parabola, the vertex of the parabola, which remember vertex is just this thing right here, does that move? and things like that. So go ahead and take some time to list out some similarities and some differences. What you can also do is, if you are not totally sure, you can get out your Chromebooks and go to Desmos, and then you can plot this equation first in a coordinate plane on Desmos, and then you can plot these various other equations to see what it actually does. If you do that, make sure that you just pay careful attention to the parentheses, okay, because that will change it, and you'll actually get to see how that changes it when you have these with no parentheses versus those with parentheses. So go ahead and take some time on Desmos to look at the similarities and the differences. So now that you've done that, you can actually look at this second test, or the second thing as well, and answer this question number 4. She decides to use her technology, and she thinks it's always a good idea to start simple. So she starts with the x squared plus 5 and graphs it along with y equals x squared in the same window. So test yourself now. Test it yourself and describe what you find. So go ahead and think about that first one, or excuse me, the last one that you did. What happened? What changed? So what you should observe is that if the original x squared parabola kind of looks like this, these are just sketches, so don't take them with or do take them with a grain of salt. The x squared plus 5 should look like this, right? Hopefully that's what you got. So it should move up 5, right? So knowing that things make a lot more sense with more representations, Optima actually tries a few more examples, like y equals x squared plus 2 and y equals x squared minus 3. Looking at both a table and a graph for each, which you can use Desmos for. There is a table portion of Desmos that you can use. So, using both of those, what conclusion can you draw about the effect of adding or subtracting a number to y equals x squared? So, out here like this, outside of parentheses, outside of the square, what is the movement that happens to the parent function of y equals x squared? What you should do now is actually write these tables down here, okay, and make some quick sketches of the graphs as well. And then, and not in your notebook, instead you'll just write them here. And now you would also want to say, and I want you to do this on your own for just a second, what does that k plus or minus k, what does that do to our function? Okay, so take a minute, pause the video again here, and see what happens with the addition or subtraction of k. So hopefully what you found is that the addition of k, just like up here, the addition of k, it moves up k, right? It moves up a factor of k, or the digits of k. The subtraction of k moves the entire function down a factor of k. So when you did your x squared minus 3, all of your values just went down 3 from the parent function. When you did x squared plus 2, all of your values went up 2 from the parent function. So after her amazing success with the last problem, Optima decided to look at what happens with the addition and subtraction inside parentheses, or as she says it, adding to the x before it gets squared. Remember, that would be in terms of the side lengths, right? So now use your technology to decide the effect of h in the equation y equals x plus h squared, quantity squared, and y equals x minus h, quantity squared. So now you get to choose some specific numbers, so maybe try y equals x plus 3 quantity squared, or some other various numbers, okay? I want you to do 2 of each, all right? So this can be one of them, but now pick another positive value, and then I want you to pick 2 negative values. Okay, so 2 negative values. And I want you to create tables for those and look at what it does, okay? So hopefully what you found is that this moves left to right, okay? So what we should have found out is if we have a plus 3 within the parentheses, okay, like this first one, that actually moves it. So when we have a negative h, or a positive h, excuse me, it moves it to the left that number of places, right? When we had a negative h, it moved it to the right that number of places. Okay, so it's a little tricky. It's a little different than the up and down. Left and right actually is opposite of what you would expect, right? Because the positive moves left and the negative moves right. So Optima thought that number 6 was very tricky and hoped that multiplication was going to be more straightforward. So she decided to start simple by multiplying by a -1. So she begins with y equals negative x squared. So what you should do now is take a minute, predict, and even talk at your table, predict what effect is going to happen, and then test it and think about why does it have this effect. Go ahead and pause here and try it out. Okay, so now that you've tried it out, and you hopefully have an idea, right, it actually moves the parabola to face downward, or it reflects it to face downward, okay? And it should be right at the origin-ish. And just make a real thick line there. There we go, at the origin, okay? So if we think about why that's happening, any x squared value is a positive number, right? But when we do a negative in front of that x squared value, that positive number is negated, right? So now everything is on the lower two quadrants here of our graph. Okay, so this actually then becomes a negative number, not a positive number. Okay, so that's why it has the effect it does. Now Optima is encouraged because that one was a little easier, so she decides to end her investigation for the day by determining the effect of a multiplier a in the equation y equals a times x squared. Using both positive and negative numbers, fractions, and integers, create at least 4 tables and matching graphs to determine the effect of the multiplier. So go ahead and pick some, make sure that you have some fractions in there, so pick some and then test it using your technology and see what happens, okay? See what changes. So pause the video here and see what happens. Now that you have 4 representations, what you should always find is that negative numbers will always open downward when you have a is a negative number, right? And positive numbers always open upward. Now, when you have multipliers, what you should have found is that your parabola gets skinnier, okay? And when you have multipliers that are fractions, or if you're dividing, which is the same thing as multiplying by a fraction, right? So let's say you have 1/3, okay? That should be a little squattier of a parabola, okay? Not quite as steep as the parent function parabola. So it's a little squattier, whereas this one is steeper, okay? All right, that is all we have for 2.1. Go ahead and start working on your homework, and we will see you again tomorrow for 2.2.